this O-physics simulation, and I want to take it away and come back to the paper. If we come back to the paper, but with the idea from that O-physics simulation, then let's just say, and I'm going to keep the same orientation as our page right now. I'm not going to try and go sideways like the same orientation as the simulator. But if we have two sources, we're going to call this source 1 and source 2. Two light sources. And I'll just for consistency, I'll call these guys light source 1 and light source 2 as well. These two light sources, if I want to project light onto a screen where there's a point in space. So I'm just going to call this my test point. And that would be for our scenario, a point on a screen. I want to draw a straight line connecting source 1 to that point and a straight line path from source 2 to that point. Hey presto. And if I do that, I want to draw my wave, positive, negative. Now wait till I draw this because I want you guys to have the same thing as me. And I'm going to label, instead of dots for peaks like was in the simulator, I'm going to put plus signs. Instead of troughs, I'll put minus signs, okay? So that we can see where the peaks and the troughs are for that wave. Because what we're doing is looking kind of from overhead at a wave that's being illustrated from the side. So we're kind of mashing our dimensions together here because it's hard to draw three-dimensionally on paper. That's all it really is. And if I have, yes, sir?
Is it supposed to be off-centered?
Yep, totally intended to be off-centered because the light traveling from source 1 to the point has to travel a little bit of a different distance than the light traveling from source 2 to the point. And as a consequence, that light is not going to fit in as many wavelengths. In fact, peak, trough, peak, if this was a peak and this was a trough and this is a peak, at the point where they meet up, notice that a peak and a trough have met with each other. That's how we're reading this illustration. And so if a peak and a trough meet each other, that's destructive interference. We're illustrating a destructive interference situation. And so we're saying that there's this path, PS1, the length from the point to source 1. And there's this other path, PS2, the length of the path from that point to source 2. And the difference between, now the line over top of them means that I'm saying that PS1 is one line segment and PS2 is another line segment. The difference between the lengths of those two line segments is going to be equal to how much those waves have fallen out of phase with one another, because the extra travel distance threw them out of phase with one another. Okay. Now I'm going to gift this equation to you, and you can noodle it out, but we're going to say that whenever we have destructive interference, it's going to be phase shifted so that some fraction of a half wavelength is the offset. And the way that we're going to achieve that is having a binomial coefficient of n minus a half times lambda, because that n minus a half times lambda, you can try subbing in different n equals 1. Here, I'll say we're going to let n equal 1, 2, 3, 4, an integer. You can try subbing in n equals all those different values, yada, yada, yada. But all those different values are going to represent coefficients in front of lambda that's going to offset these waves sufficiently to throw them out of phase with each other for destructive interference to occur. Okay? So like if n equals 1, n minus 1 is a half. If n equals 2, 2 minus a half is 1.5. 3 minus a half, you'd be phase shifting it by 2.5 wavelengths. Every time you phase shift it by half, 1.5, 2.5 wavelengths, they're going to line up so that destructive interference occurs. And so that's what that condition is telling us. We're saying this condition is the condition for destructive interference. And so this idea of waves being phase shifted, I am sure that my math friend would talk about waves being translated sideways. Can you imagine him saying that? You know, translated in the x direction? We're going to call it phase shifting. And people say that path length difference causes this because they have to travel different distances. Now, likewise, if I were to take another test point, and I have source 1 and I have source 2, and I have another point, it doesn't have to be like halfway in the middle, but I'm going to choose a spot that's kind of halfway in the middle, and we say, hey, the wave from this one, well, maybe it doesn't have to, maybe I won't even make it halfway in the middle because I don't want to be misleading. Maybe I'll put it over here somewhere off to the side, put a point here, and I say, if that wave has to travel that path and this wave has to travel this path, again, we're going to start from source 1 and from source 2, but we have to travel different distances because they're traveling different pathways through life. This one fits positive, negative, positive, negative. This one, on the other hand, only fits a positive and a negative. But if I label this up plus, minus, and I label this one up plus, minus, notice that both of them get their negative amplitude to the same spot at the same time. And that means constructive interference. And so we can come up with a constructive interference equation constraint that says PS1, or when PS1 minus PS2, I'll put a line segment over top, is equal to m times lambda, where m takes on values of 1, 2, 3, 4, an integer. I could say positive integers because they're counts, right? Positive integer. Then we're going to get constructive interference. And check this out. For the diagram that I showed, those two waves have been thrown off by a whole wavelength. So that's when m would be equal to 1. And of course, when m was equal to 2, they'd be thrown off by 2 whole wavelengths, but that would put them back in sync again, right? And so that would be constructive interference. And again, it's due to path length difference. And when I say path length difference, I mean the length of the path that they traveled is different. It's like using a word in its own definition almost. But then I also want to point out this. When I say n, I intentionally used n for the destructive interference integers because that's where the nodal points will happen. And nodal, just like in sound waves, means destructive interference, nodes, as opposed to antinodes. Now, I'm not going to use a for antinodes. I'm going to use m as the other integer. Now, typically people use n, m, and l as integers when they're making up coefficients in math and in physics. I'm going to use m because of that tradition, but I also want to use it as a memory aid because I'm going to use m as where the maximum, plural of maximum is maxima, where the maxima occur. Okay, so as a memory aid, we're going to use m for the integers for maxima. Now, you won't see that in every textbook, but I like using the n's and m's that way just so we keep them straight. You know, it's because otherwise you got n being used for two different conditions that are actually kind of opposites of each other, and that doesn't seem, well, that just seems poor to me.